Workshop in Andalusia with the company Incessant Youth. And I am Laurence Rickerman from Telecom Paris in Paris, France. And now Telecom Paris belongs to University Paris-Saclay. So Francisco, you have now about 45 minutes to present your thesis.
Okay. So good morning, everyone. Thank you for this introduction. I'm going to present the work of my thesis called Probabilistic Graphical Models for Document Analysis, developed here at the CBC under the supervision of Oriol Ramos Terrades. So this is the outline of this presentation. In the first place, I will introduce the ambit of this thesis and the set of problems that we are going to address, which are document layout analysis and handwritten text-line segmentation. Then I will present the set of contributions performed for these two problems, and finally I will draw some conclusions and closing remarks. So in human history, the written word and documents has been the main way to transmit information between people and generations. And it was especially in the last century where the amount of information in paper documents increased considerably, especially in the ambit of the business activity, where in fact it is estimated that more than 80% of the current volume of paper documents belongs to this ambit. So in most cases, in all these stored documents, there is information that can be relevant for the company activity, and there is this need for their part to be able to process and extract in order to analyze this information for a better management of this information. So this situation has been also seen in the context of ancient collections of documents, where there are collections with invaluable contents which are object to conduct research studies. So in order to conduct these studies, it is necessary to extract information, and in order to extract the information, we need methods that are capable to analyze the structure of a particular document and being able to detect the different parts that compose it in order to identify the area of the document where the information of interest is located. So in document analysis, we refer to this task as layout analysis. So this process of analysis of the structure can be done at different levels of abstraction, as for instance, we can be interested in identifying physical entities by defining homogeneous areas of the image or defining the region boundaries of these regions. But for some tasks, can be also convenient to assign a meaningful label to each of these regions in order to define the role of these entities within the document. So this process of analysis can be also focused in the detection of other kind of more low-level entities, as can be the case of the set of lines that compose the document, which is called this particular problem, handwritten text line segmentation. So usually we want to perform a pixel-level segmentation of the page, which can be useful for many other posterior processes as the recognition of this text. Also, this task complements the full layout analysis of the documents, in the sense that we detect all the regions, and then we can also finish this analysis by detecting the set of lines, and also in the opposite way, the detection of the lines can be also a clue for the detection of the more high-level structure of the page. So this problem, for the case of handwriting text has some additional challenges regarding the existence of touching characters or curved lines or other situations that are common in the writing styles of the people. So these are two well-known problems in the community of document analysis, and there have been developed many approaches. There are common approaches as bottom-up or top-down methods that has produced quite good results when the documents are or have some special characteristics, because some of them are commonly based on assumptions about some space between the regions or particular characteristics of the text. But the application of these kind of methods in documents with more complex layouts can be no longer suitable. So for instance, in this kind of documents, we as humans perhaps can interpret some kind of a structure as a set of columns or different blocks of text, or a particular structure that is replicated through the page. But for general methods, the existence of overlapping areas or other kind of elements can be an inconvenience for each application. So in this thesis, we focus on the analysis of this kind of complex layouts, and we are proposed to do it by proposing models that are capable to include this prior knowledge that we can have about this kind of collections, and encode this prior knowledge by modeling the set of contextual relations that we know that appear within the page. For instance, here we can model the set of structural relations that we know that are between the three different parts that compose this kind of records, and also the structural dependencies that are in this kind of documents. So we also want to focus in the detection of the handwritten part of this kind of this type of documents, that are administrative documents where the handwritten annotations can be located at any area of the image with different styles, orientations, or coming from different writers. So the main objectives of this thesis is to propose new solutions to the problem of layout analysis and handwritten text line segmentation based on modeling these sources of contextual information that allow us to encode this prior knowledge that we may have about the structure, and using this information we want to reinforce the detection of the different entities and also the characterization of the structure. And we propose to do this using mainly probabilistic models that offer a natural framework in order to learn and encode this kind of information. So now I will present the first part concerning the layout analysis problem. I will define the three main contributions of this part, then the experimental evaluations, and finally the conclusions of this part. So the first contribution is a model based on segmentation, using a model based on conditional random field. This is a model widely used in document analysis by its ability to model these contextual relations between neighbor areas that produce a smoothing effect that can be convenient for some tasks as image restoration or segmentation. So the use of this kind of technique in document analysis has been focused in the detection of textual areas with respect to the background or also image areas, but in order to encode the logical characterization of these regions, it is usually necessary to concatenate several levels of classifications or to define more complex structures of the conditional random field. So what we propose here is to use a type of contextual information that captures the spatial relationships between the different classes that we want to model, and using this information we want to be able to better encode the logical role of the entities. So the main contribution of this part is this definition of a relative location prior that we are going to add to the layout analysis process in order to reinforce this logical analysis. So the model that we propose is we first segment divide the image in a set of cells, and we want to find the best configuration of the labels for each of these cells. We propose a common pairwise conditional random field where the problem is defined as a maximum a posteriori problem, where we want to obtain the configurations of this label that maximizes this probability. And the information that we are going to encode within this model will be given by a unary term, that is where we are going to encode this relative location prior in the form of a set of relative location features. And also we are going to use an additional texture descriptor that will be based in the Gabor transform. So also we are going to model this pairwise potential, that is the term that will encode this smoothing effect, and we are going to use a common Potts model for this term. So in order to encode these relative location features, we based in the work of Stephen Woolk in the segmentation of real scene images. And in order to encode these features, we first need to compute these probability maps that are a map where defines the location where it's more likely to find elements of one class with respect to elements of another class in a normalized space. And then using this information of the probability maps and an initial classification, we can encode a measure for each cell that contains the information sent by all the other cells with a measure of how likely is to label this particular cell with respect to its position and the position with respect to the rest. So in the case of this image that I showed at the introduction, here we can see the area that is more likely to label this kind of elements, and also the area of the center. So in order to encode this information within the conditional random field framework, we can separate between different sources of this information, and also combine it with this texture descriptor that we use at the same time for obtaining the initial labeling, in order to encode the final probability that will be included within the conditional random field. So with this, in this contribution, we have presented a framework based on conditional random field that is not necessary to concatenate other levels of classification, because we are encoding this source of contextual information that captures the spatial relations between the elements, and we are able to reinforce the classification results and the logical description of the elements. However, using this kind of method, we cannot still represent hierarchical relations that we know that appear in the document, and to specify other clues of the document structure that perhaps for some tasks can be convenient to do it. And also, it will be interesting to provide a quality measure of the probability as a quality of the segmentation of a particular structure within the page, and also the global segmentation. So this leads us to the second contribution, that is a model based on bidimensional probabilistic context-free grammars. These kind of models are a method for syntactic pattern recognition that has been previously used for the decoding of strings, and in the case of layout analysis has been previously used in the form of simple probabilistic context-free grammar to decode the image structure in both directions and then combining the results, or by incorporating other processes as the classification of the initial entities, and then use a grammar to find the best parsing according to these entities. So what we propose here is to define a model based on bidimensional probabilistic context-free grammars that is able to model the hierarchical relations in the page, and also the structural relations that we know that that appear in the page. And we are going to define a full probabilistic framework that guide this process from the low level at cell level of the image to define the full analysis of the structure. So the main contribution is this formal probabilistic model that we are going to present now for structure detection, and the process that we deal with all the learning process of all the parts that we want to model, and the interpretation problem given a particular document. So a bidimensional probabilistic context-free grammar is defined as a regular grammar, with the difference that now the non-terminal symbols will account for bidimensional regions on the document. Then we also have the terminal symbols, the star symbol of the grammar that will be the whole page, and then a set of rules linked with a probability function where we are going to encode this structure of the page, and we are going to model order hierarchical and structural relations that we know that appear here. So we can also define we can parameterize these rules in order to define the domain of adaptation of these rules. We can define, for instance, horizontal and vertical productions, and we can also define some spatial relations constraints for this kind of rules, as for instance that in order to combine two different regions they have to be of the same width or the same height, but also it can be modeled any other feature that results convenient to define the structure of the document. So given a problem, once we have defined this grammar that defines it, the objective is to find the most likely parsing according to this model. So we are going to do this using an algorithm based on the CYK algorithm extended for bidimensional structures that we also extended by including our probabilistic measures. So in this algorithm, the objective is to fill this table where each entry will be the probability that a particular non-terminal symbols account for or results in a region of a particular size. So the algorithm starts in the initial symbol of the grammar, that will be the whole page, and then always then the size of this subproblem is larger than 1 by 1, using the cell level as reference. That means that we can apply a rule that divides this problem into particular subproblems with a particular probability. So this probability will be given by several probability distributions. In the first place, we model this probability that will be the probability that at a particular non-terminal region has this particular size, and this will act as a pruning term in the derivation process in order to simplify and speed up the parsing process. Then we also have these rule probabilities and the probabilities of the two subproblems that at the same time will be computed with this same equation, which produce a recursive process that at the end we obtain the best parsing of a particular page. So when the size of the subproblem is of the minimum size, that is 1 by 1, the problem can be interpreted as obtaining the maximum probability of labeling this particular cell that we can use, for instance, the descriptor that we presented before, or any other result of a classifier based in any other type of feature. So also the rest of the probabilities that I presented can be learned from the training set by computing a false recognition of the ground truth. And with this model, so we have presented this probabilistic framework based on bidimensional probabilistic context-free grammar for structure detection that we can use to model these structural and hierarchical relations that we know appear in the page, and we can also retrieve the M-based solutions or the probabilistic measures of a particular structure that we have detected within the document. However, using this model, the inconvenience is that all the information has to be encoded in the grammar. We have to be sure that we are modeling the correct grammar, and it's not so flexible to introduce changes in this structure, which can be also quite computationally expensive if the structure of the page is very complex. So with the third contribution, we want to propose also another method that is capable to model these hierarchical and structural relations, and we propose to do it proposing a method based on region segmentation, where we want to find the best configuration of the regions that form the page. That we want to be this method more flexible against the structure variations and to introduce new sources of information. And also we want to compute this this probabilistic description of the documents and the dependencies between the parts. So the main contribution here is this process based on the EM algorithm for finding the base configuration of the regions, and we are going to use also a Bayesian network to factorize the probability that models the dependencies between the different parts of the model. So for this model, we propose to approximate each of the regions that compose the document with a bidimensional Gaussian distribution, where the mean will indicate the center of this region, and the covariance matrix will define the size. And these Gaussians will be based on will be defined on a random sample of pixels selected from the document, which will add or include to the model the information about the features and the location of each of these pixels. So the idea is that given a set of regions initialized in the document, we are going to run an algorithm based on the EM algorithm with the objective of finding the best configuration of these regions that better fits to the page according to the probability distribution that rules models the relation between all the elements. So to give an example of application, we rely again on this document that I showed in the introduction. So for instance here we can have some observations that can be a descriptor at pixel level and the location of these pixels, and we know we want to model or to obtain a set of regions that appear in this kind of structures. Also that these regions will be included in a set of records that we are also interested to extract, and that in a given document we are going to find a particular number of records. So in order to define the probability that relates all these elements, we rely on the dependencies that we know that are included here. For instance, that the descriptor will depend on the region that is modeling, that not all the locations will be equally likely to contain particular regions of a particular record, and also that the configuration of these regions with respect to the records will depend on the number of records that we are going to model. So this produced a factorization of this model using according to these likelihood probabilities that we can use in a maximization problem to find the best configuration of these regions. So the algorithm at the end has these steps. In the first time we will initialize for this particular collection a set of records that we want to initialize and that we want to fit. Then the set of regions that that corresponds to the different areas that we know we want to find. And then in this iterative process we are going to update in each iteration the parameters that define these regions in order to find the best configuration. So using this model we have a region estimation, a region classification model that uses this Bayesian network to model the dependencies that we know that appear in the document, and also is more robust to introduce new knowledge about the document in the sense of modeling new regions that we know that appear or other kind of information. However, it is more sensitive to initialization of the regions, and we have to add here more prior knowledge about the problem. So now I'm going to present the experimental evaluation of this part. We are going to use the common metrics for this kind of problems, that is precision, recall, and F-measure computed at pixel level. So we are going to perform experiments on this collection. This is a collection of the Barcelona Cathedral that is relevant to obtain information for demographic studies. So it's a demographic studies. So it's a real problem. The objective here is to detect the set of regions by detecting the three different parts that compose it. Also, we are going to perform some experiments on the PRIMA benchmark dataset. That is a dataset from a competition, where we are going to find the text regions with respect to non-text areas. So in this first experiment, we wanted to evaluate the contribution of these relative location features in the problem of layout analysis. We are going to compare three different inference algorithms: the GraphCut, loopabilis propagation, and an ICM algorithm. And here we see as the use of the relative location features for the three different algorithms obtain quite good improvement with respect to the use of only Gabor filters. And also here we obtain better results with the GraphCut algorithm. So we wanted to check if this improvement is also observed in a non-structured collection, as can be the PRIMA dataset. And we see that here, using relative location features, we obtain an improvement, but it's not enough high to ensure that this is statistically significant with the use of these features. Also, comparing with the other contestant methods, we obtain similar results to them on this collection. So with the second experiment, we wanted to compare these two models that encode different sources of contextual information. This is the case of the experiment that I just presented, in comparison with the bidimensional context-free grammar that encodes this particular definition of the structure of the page. So here we see, as in the case of grammar, the improvement of relative location features is not longer significant, since this was something expected, since we are already encoding the structural information of the page. And we obtain a slight improvement with respect to the other method, with the main difference that now we are able to retrieve the structural definition of the records. Also, we want to compare the behavior of the two models that encode this kind of information. We see as our third method, we obtain lower results in numerical values, but in terms of retrieving the the records, we obtain a better definition of these structures. So here we can see some qualitative results. In the case of the conditional random field model, we weren't able to identify the set of records, but in this case we were. And here we can see why we have some precision, lower precision results. We usually obtain wider regions, mainly because of the noise on this area that produce this increment of the regions, but we are able to always identify all the parts that compose the records. So in conclusion, in this part we have presented several methods for layout analysis that are able to encode this prior knowledge that we may have about the structure of the page in terms of modeling these contextual relations between the different parts. We have seen as the inclusion of relative location prior improves the detection and categorization of the regions in the models that do not explicitly specify the structure of the page. And also we have presented two other methods that can model this kind of structural relations with quite good results on the extraction in a real case. So now I'm going to present the second part of this presentation, that is regarding the problem of handwritten text line segmentation. In the first place, I will present an overview of the method. Then I will describe the two probabilistic models that we are going to, on which our method will be based, and also then I will present the experimental evaluations and final conclusions. So the objective when developing a method for handwritten text line segmentation, it is important that the method is able to be applied on different collections of documents with different characteristics, without the need of reconfiguration of the parameters or learning of different parts of the method. So also in the literature there are many methods that focus on particular problems, as can be the touching lines or curved lines, by defining heuristics or complex models to deal with this problem. And we want to develop a general method that deals with this problem by also including sources of contextual information that propose that apport to the model this information to deal with this problem. And we want to do it by modeling this probability distribution between the set of text lines and the pixels that compose it. So the main contribution of this part is this general method for handwritten text line segmentation, and this probabilistic framework that we are going to define for computing inference on this particular method and parameter learning of the parameters that we are going to define. So the main hypothesis of this method is that given a particular text line, if we know the pixels that compose it, we can estimate a regression line through these pixels that is a good estimate of the location of this line. And then we can also define a probability distribution that relates this set of pixels with the set of lines that we are fitting. The problem is, of course, that we don't know this information. So what we propose is to use a version of the EM algorithm in order to find the best configuration of this regression line that in each iteration fits better the points of the line according to a probability distribution that we want to model that relates all this information. So as a first model for modeling this probabilistic probability distribution, we propose a model based on computing local Gaussian distributions for each line using according to the parameters that define the regression line. So in this case, the problem will be in each iteration to update the parameters that define each of the regression line, that is the skew, the location, and the variance of this regression line, according to this Gaussian distribution that is present with this regression line. The problem is that using just a linear approach is no maybe cannot be enough precise in order to deal with the common challenges, and we require of additional information in order to do this. Also here we are only producing this fitting process based on local information at pixel level, which can be not enough informative to produce a best definition of the lines. And also here we are not controlling the length of the regression lines, which can be a problem in the case that we try to segment lines from 2 consecutive text paragraphs or in complex layouts. So we propose to deal with these issues with our second model, and we are going to do this by modeling the joint probability distribution between the pixels and the set of lines that we want to fit using a Markov random field framework. So here the structure of this model will be defined by the Delaunay triangulation computed in a set of random pixels from the textual part. And in this way we can model this smoothing effect that we have in the previous part using conditional random fields, but also we can incorporate new sources of information that relates all these elements. So in order to factorize this model, we can define 2 different factors. In the first place, a factor that relates the observations with the label, that will be the corresponding regression line, that in this case will be equivalent to the first model. And then we can also model some new features regarding the relation between the hidden variables. So in the case of the first type of factors, we can model in this factor different feature functions that encodes the measure of how well a particular pixel fits into a particular regression line. And we are going also to expand the representation of the lines with 2 new parameters that will control by a new Gaussian function the length of the line. So in these terms we can encode a set of local fitting functions that can be the fitting to the regression line or any other function that we can guess according to the problem. And also, any other description at pixel level that indicates how well it fits to a particular line. So, in the second part of the factorization, here we can model the relations between the different levels and the different lines. We can encode feature functions as, for instance, the probability of each line, and also this pairwise information that will be as this smoothing effect, and also will provide information about for each pixel about the rest of the network. So at the end, the algorithm is based in these steps. Initially, we are going to initialize the set of lines according to several processes. We want to initialize a set of regression lines, and also to initialize the set of parameters of the probability of the lines and pairwise parameters. And then in each step of the EM algorithm, we will update these parameters that cannot be done in the same way that in the parameters of the regression line. So we are going to incorporate the update of these parameters within the inference process of the algorithm. And then we compute also the inference of this model by using a message passing algorithm based on the generalized belief propagation, where each element will receive the information from the rest of the neighbors in order to reinforce the decision of B level with a particular regression line. So in each iteration, using this information result of the inference on the model, we will update the parameters of the line in order to find the best configuration. So as initial and post-process steps, we define a basic text region segmentation in order to, based on cuts on the Delaunay triangulation, in order to isolate different components, and we can then use our model on each of these parts, which adds some generalization to and more strongness to the method. Also, as a post-process step, it can be necessary to remove some excess of regression lines, and also we incorporated a step to merge different regression lines in order to account for curved regions or other kind of structure of the lines. So the experimental evaluation, here we have used the same measures used than in the ICDAR competition, based on the computation of one-to-one matches between the results and the ground truth, and then 3 indicators based on these one-to-one matches, that are the detection rate, the recognition accuracy, and the F measure of the results obtained. So we are going to perform experiments on 4 different collections. In the first place, we are going to use the ICDAR 2009 and 2013 data sets of the competitions, that are binary scan documents written from several writers, different languages, and free of graphical contents, that contains a set of 200 and 150 images. Then we also want to perform experiments on this historical collection dataset, that is the George Washington dataset, written in English by different writers. We are going to work in a binarized layer, and in this case we have also some non-textual elements as some stamps or separator lines. Finally, we are going to perform experiments on a real dataset of administrative documents with annotations, which contains annotated documents from bank checks, annotated invoices, company letters, or other kind of documents with annotations that have this kind of layouts and distribution of the lines. So the full dataset is composed by 433 images, and we are going to work on the handwritten layer separated from the machine printed layer. So in the results of on the ICDAR 2009 dataset, we see that we have an improvement with respect to our first method, and also that we are close to the top methods on the competitions. And I have to remember here that we have not fixed any parameters to fix to the particularities of this dataset. And in the case of the ICDAR 2013, we obtained some similar results than before. We obtained a significant improvement using our second model that is up to the top methods, without the need or without taking special considerations to the particularities of this dataset. So here we can see some qualitative results with, for instance, slightly curved lines or some cramped text that is well segmented. Here the results on the George Washington dataset. We also obtained improvement with respect to our first model, and in this case we are able to identify separately these separator lines that in the ground truth are linked to a particular line, which slightly reduce the numerical results, but in views of recognition processes, it can be more convenient to be able to detect this type of lines. So regarding the last experiment, we also see in this trend that we obtain better results with incorporation of this contextual information. And here we have some qualitative results. We can identify this even with a linear approach. We can identify these 2 different segments of text, and also we detect any source of information that is present in the document. Here we have more qualitative results on this data set. We can also find lines in broken lines with the result of the scanning process, or the existence of these kind of elements also do not affect to the overlapping of the lines. And we are able to detect also signatures and in different regions of the document. So in conclusion, we have presented here a general method for handwritten text line segmentation that is able to to be run across different collections without the need of particular tuning of parameters or retraining any part of the model. We have achieved promising results using just a simple linear approach by including a source of contextual information within the model, and also that using this contextual information and the distribution of the Markov random field, we can deal with the common challenges of the task, as the case of touching characters or slightly curved lines, without the need of particular configuration of the parameters. So now I will draw some general conclusions of this thesis. So in this thesis we have presented several methods for the task of layout analysis and handwritten text line segmentation, with the objective of encoding prior knowledge that we may have about the problem in the form of contextual relations and contextual these structural relations and hierarchical relations, and we have do it using a set of probabilistic graphical models and probabilistic models that provides a natural framework for this kind of problems. So we have proposed the use of relative location prior in order to reinforce the detection results and the characterization of the logical role, and we have seen as in the case of methods that do not account for explicit structure of the page, it can be a good descriptor. And also we have presented two different methods for that account for these structural and hierarchical relations with good results in extractions in a real data set. So regarding the text line segmentation, we have proposed a general methods for handwritten text line segmentation, where we encode contextual information in order to deal with the common challenges of the task, and it's a model that can be easily extensible with other kind of feature functions that can add new information at local or pairwise level, and our method is able to be run with good results across different collections without the need of parameter tuning. Also, we have evaluated this problem in a business-oriented real application for the segmentation of handwritten annotations with quite good results in a real environment. So I think that the research on this thesis has opened some new research line. For instance, as a next steps, we can be interested in performing a full layout analysis by combining the detection of the layout with the segmentation of the line within the same framework. Also, it can be useful to encode new sources of information within our Markov random field framework from other document analysis tasks, for instance, in order to include within the same text line segmentation model the separation between the handwritten layer and the machine printed layer or any other task. And also, as more technical suggestions, maybe to move to a higher regression model can be better to deal with more complex configurations of the line. And also, it will be interesting to be able to combine or discard regions in the EM-based model in order to account for more complex structure collections. So, as the result of this work, we have produced several publications in international journals and international conferences. And also, an important part of this thesis was a partnership with a company, with a French company, with its ITSOF and JUICE, which has produced several prototypes implementations and the final integrations of the handwritten text line segmentation method within the company services. So here I will conclude this presentation, and now I will be pleased to answer all your questions. Thank you very much.
Thank you for this presentation. It's now time for questions. So first I will Simone Marina and and we will ask the first question.
Okay. Thank you for your presentation.
Thank you.
Very clear, like your thesis, because it's related to the thesis, because it's very well put together.
Thank you.
Well, I have several questions, so maybe I need to select some. Sorry. Okay, first I have a question related to your latest slide. So you mentioned...
Which?
No, it's bad last. Never mind.
Okay.
Okay, the very first is some of these techniques are computationally expensive. So can you give us some figures about the time required by several tasks? And this is related to the second part of the question. You implemented these techniques, in which language you implemented?
Okay. So regarding the second part of the question, all the implementation of the method of the handwritten text line segmentation, we did all the implementation, all the different parts, the initialization and all the inference algorithm were computed with our own implementation using C++. And in terms of times, I think I have a table in the manuscript. Maybe I can open here.
Okay, you can.
Well, I add some information about the time using different percentage of the random set of pixels selected, and well, it is true that that can be computationally expensive, but I think it's in the terms of acceptability of the industrial applications, because we get some, for the results that I show in the manuscript were for quite complex documents, as for instance the case of the documents in the ICDAR competitions that include many set of lines, but in other real applications, and as the case of these administrative documents, the density of the lines is lower, so the running time is quite fast actually, but it is true that it can be computationally expensive depending the type of document.
Yeah.
Well, regarding the other methods, all the grammar for decoding the page was more, the more computationally expensive part was the learning. Then the process for a page, I think, was around 30 seconds, more or less. I don't exactly remember right now. And the rest of the models were quite fast. Only to compute these probability maps, the process took several hours to do all the computations, but then in execution time was not really slow.
And the integration with the software architecture of the company, for instance, was easy?
Well, this part was done more in a parallel environment, but according to their specifications of the type of modularity of the functions, and also the kind of libraries that I could use, but it was quite open, using OpenCV libraries or Boost. I didn't require of other specialized libraries. But then the integration, it's on their part, but I think it's all quite good modulated and was quite simple to.
Okay.
The key was the communication, between the two parts.
Exactly. So another question, more technical, perhaps related to the line finding, okay, to the second part, and basically you use line regression, okay.
Yes.
And you mentioned that you could in the future, here in the slides, use higher order regression models, but maybe there are cases where you can still use linear regression, but maybe have a quite piecewise approximation of the line. And we saw some examples where you have separated words, and you have not aligned lines.
Yeah, for instance,
the previous one, like in this case. But as far as I understood, in the handwritten document from the collection, you always have a single line to the full text line. Is it possible to change the model, still, or maybe it's already working that way, still having linear interpolation but with piecewise interpolation, something like this?
Yes. Actually, we consider this kind of piecewise interpolation because what we do at the beginning is to initialize a set of regression lines that are more specifically are regression segments. So it can be as in this case that we for a particular image we initialize more segments than actual lines are. So at the end in the process, each of these segments will fit particular lines. So as in this case, each of the segments can end up fitting a part of this piecewise line in the case of that we have some curved lines. So so the case is that we initialize more lines than the expected in order to be able to account for this kind of situations.
But when you have these are administrative documents. When you have the benchmark, in most cases, it's a page full of text lines. And if I read in the cases, you initialize by looking for expected number of lines.
Yeah.
So basically, you have, if I understood well, an interpolation line for each text line. So it happened in some cases that you had more than one line interpolation or line for a given text line, or
it can happen that I have that for the same text line I have several segments that are fitting the same line.
But you discard some.
But in this case, it can happen that at the end one of these parts end up with a very low probability and I discard it. And also we have a process to merge these situations. We identify the situations where this is happening and then we merge and unify within the same level.
Yeah.
But it can happen, sorry.
So if you have a card line like this, what happens?
We tolerate a certain degree of curvature, no? But if we have a curved line, maybe in the initialization we initialize several segments, and then the line can happen two situations that it's fitting with different segments and that we are not able to detect and unify in the same level, or that we just identify the different words or group of words in each segment, which for recognition task can be not a bad choice, but actually we are getting a bad description of the page, no? But we are encoding this, we are detecting these lines using different segments.
Okay. Well, a very little. Another small question.
Yeah.
And now this is more general. In the second task it's clear you had an application related to administrative documents. Did you try to use the techniques of layout analysis in the first part also to administrative documents as well?
For the line segmentation or to the text line? Yeah,
maybe for instance in that case you can, if you have letters, maybe you can figure out similar tasks like say the sender and this is the receiver.
Well, as the objective of the methods for layout, for the part of layout, was more to encode this prior knowledge of complex structures, we haven't applied this kind of methods for this kind of administrative documents. But also,
but you think it might be possible?
Well, in fact, it can be possible. We use the similar EM process to fit the lines or fit the regions, so maybe we can do somehow the combination of these two parts. And well, the thing is that in this case of administrative documents, we have very different layouts to the collection. Now we can have bank checks or invoices, so it's difficult to, since our method focus on general
yes, but if, for instance, you just focus on this is a letter, these are letters, or letters, maybe you can find
some letters
subsets where the center is always, nearly always in some place, the signature is at the end of
this can be encoded, and using our relative location descriptor, maybe it can be useful to produce the layout, the logical analysis of this kind of pages. It can be applied.
Okay.
Okay, thank you, Simone.
Thank you.
I ask now Joseph to ask some questions.
Thank you. Well, Frank, thank you for the nice presentation. You did it in exactly 45 minutes.
Yeah, I think it was running.
And well, congratulations for this nice piece of work. I think you made some interesting contributions with a very robust mathematical or methodological basis, but more than this, with proven practical application, because at the end both parts were applied on real cases. The second one, of course, with the collaboration of Microsoft, but the first one at the end was a real project that we are working on, and we used your technologies at the end that were generated. Well, let me just address some questions we have, of course, discussed a lot during your thesis. Well, maybe let me start by the details, and then I will end by general questions. Well, first of all, for the layout segmentation, well, and also the second part as well, you have some of the approaches are pixel-based approaches. You start from pixels, labeling pixels and defining the rules or the context from the pixels. Taking into account the type of the images you are working with, you know that you have documents, you have text there, handwritten, printed. Why not starting from a higher level and doing maybe a graph segmentation, I don't know, connected components, superpixels, regions, and then define the model, define the context for these higher level entities?
Well, in the first place, regarding the use of other techniques as for this lower level segmentation in superpixels and so on. At the beginning, we tried, especially for the case of the Barcelona Cathedral, to extract the superpixels instead of using just texture descriptor and the patches. But the thing is that maybe for the description of the local information, the resulting superpixels, I think, was not well defined. The boundaries of these superpixels took regions that then, in order to combine it and find the relations between them, was not so clear. Maybe we were expecting that we extract more superpixels containing the connected components or particular regions of the text, but the final definition of the superpixels was not so good to do this. And then in the second place, starting from already detected regions and using to then produce the full analysis of the page has been previously done, and is the common approach for newspapers or other kind of common documents. But for this case, I think that it's more important to base the initial analysis at more low level in order to then being able to group and analyze these relations between the different parts. But if you start from an initial analysis, maybe there can be some errors in the characterization of these regions because of the existence of overlappings and other elements. So I think it's better not to rely on already segmented or high-level entities, but to being able to include in the model the information necessary to produce a better analysis starting from low level to high level.
Okay. How still for the layout segmentation part? The experiments you showed us with the marriage records, you are working with 3 classes, no? The left part, the central part, and the right one. How sensitive is the model? If you, or how scalable is the model if you would like to segment documents with 10 types of blocks, for example?
Well, I think all the methods are quite scalable at this level. Always done, and this prior knowledge that we can add about these different blocks is good knowledge to guide the process. In the case of the grammar, maybe the resulting grammar is more complex, which results in a more computational time for learning this structure and this probability. But I think all the models can be scalable to detect more complex structures. Always that we have this semi-structured information of the regions.
Are the methods combinable? So, for example, the probabilistic grammar, I think it's like a higher level description, no? And the first method, the conditional random field method, it's more low level. So, could you combine somehow, put, for example, some grammatical rules on the top and then start from blocks extracted from the other method?
Yes, this is something that the method allow it quite easily. The terminal symbols now we are just using this definition of the cell level classification, but can be also defined on a previously detected regions using our previous model based on conditional random fields. Use this as a terminal symbols, and then use a grammar on the top of this information. And also, for the problem of text line segmentation, can be also defining a set of grammar according to these detected lines, then define a grammar that accounts for the full description of the page. Although it maybe can be quite complex, but they are quite combinable, I think.
Okay, let me move to the second part, the line segmentation part. I was wondering, seeing the figures you showed to illustrate the method. When you compute the regression line, it looks like the key points that you are using could influence a lot on you have a handwritten text, or you have some pixels that are in the ascenders of the sender, and depending on especially when the lines are maybe not long, maybe there are some key points or some pixels that influence a lot on the deviation of this line. Have you tested other key points, or like maximum, minimum, or corners?
Yes. Actually, this was something that we have to account at the beginning. In the first experiments, we just used the centroid of the connected components, but we realized that it was very few information. So this outlier effect that you are commenting, in the case of long lines, as you said, is not so representative. But in the case of more short lines, it can produce difference of this skew, but not so important to affect the detection of the line. So at the end we choose this random sample of points on the textual image, and we are sure that in the central part we are going to have more density of these points, with which allows to avoid this kind of effect. Also in our fitting functions, we also focus in the central part. We give more weight to the points that are located in this part. And regarding if we consider to use other kind of distribution of these points, actually it is convenient to have a wide distribution of these points in order to have a better definition of all the grid of the Markov random field, in order to have a better distribution of the information through the network. So the use of other more informative points, or more intelligent way to choose this set of points, I think wouldn't have a real impact on the results, because what we want here is to have a proper distribution of this point, a representation of that better represents the line. So I think it's not important to have a quite intelligent process to choose these pixels, but it could be convenient to test maybe some features in the future.
Thinking in the application, one of the probably most interesting parts of this application is for annotations, not just
Full
letters with perfect lines, horizontal lines, and so on, but to detect or segment the site annotations that you have, that usually are in different orientations, or even not a straight line, it's curved line, and so on. You showed some results that qualitative results that the method works quite well. But I was wondering, it's not probably a question on the current status of your contribution, but maybe thinking in a future improvement on a two-steps process. So after detecting lines, especially when you have lines that belong to site annotations and so on, probably the detection of one line that maybe is a diagonal orientation can reinforce the detection of another line. So I was wondering if a post process that maybe going to the first part, a post process that once you have detected individual lines, tries to group lines depending on some other features like orientations, even the features that are extracted from the pixels, so it's the same text, the same writing. What do you think about this context based on the other lines that have been detected nearby?
Yes, in views of extending the analysis to also group these lines in order to find the definition of the layout. I think it's a good question, and it's a good idea. And actually, in our model, we can encode within this within the local functions also this kind of associations and relations between the lines. So it can be a good thing to do, and I think our model allows to do it with the current implementation, allows to do some operations like this. So yes.
Okay. Well, maybe a last question that is also a more future work or general question. Can you go to slide? Example, slide 9.
9?
Yeah. Well, the first you have an example.
This?
No, the previous one, I think. Yeah, this one. Yeah. The right one. If we try to visually segment this page, we can guess that there are columns and maybe some blocks, but I have the feeling that we need to read to understand that this is really a block, or this is really I don't know, a record, or it depends on the content. So it's again this chicken and egg problem, segment to recognize or recognize to segment. So what do you think about combining at least the two methods? So sometimes the recognition of some special words at least, so I'm thinking in doing some kind of word spotting or just handwriting recognition, can guide the segmentation process, because we understand that this is a name or this is a word that is repeated several times regularly in the page. So if this word is repeated several times in the page, probably it means that there is a repetitive block based on this text, and probably it's what humans we do. We try to understand the layout also based on the words that we read, or there is a graphical part the same. So have you thought about this, about defining this include, or how difficult would be to include in the models you have to define the context, not just physical context in terms of the position of things or hierarchical, but also the context based on the content, based on the interpretation of the semantics or the reading of the parts.
Yes, well, actually, what you see, our methods try to encode or are focused on including this contextual information more at a structural level, but it is true that there are many other sources of information, of contextual information that can be used, as you said, in the case of word spotting thing. So actually, there are some other works in this kind of collections that go in this direction. So I think, especially in the case of the model based on grammars, this kind of information can be encoded easily, and also will be quite useful to improve the detection process. But yes, it can be interesting to also try to model the context of the context, no, at this more deep level, and yes, can be very interesting. And also regarding the information that you can, what you say, that it is necessary to read and to understand this process. Well, this kind of documents, it puts in relevance the need of a good communication between different parts of the different scientific parts, no, as the linguistic or demographic people or historians, in order to be able to define these new contextual relations that we as computer engineers cannot see, but it's important to have this communication. But yes, I think including this kind of source, it can be very interesting, and for future stage of this research, I think I would go in this direction, because I think that this contextual information is everything in order to analyze this kind of layouts.
Okay, so I think I will stop here. Just let me maybe say last comment. You are I would say the last one of what I call the golden generation of the group. There are new generations that will come, but you were, maybe 5-6 people that you arrived together around 2010, 2011, I think, and you all contributed a lot to the excellent working atmosphere in the group, also making some good contributions that for sure open new research lines for the new generation. But I hope they will also give the same results. So So I only have to say thank you, not just for the scientific contributions, but also for the social contributions, and good luck in the continuation in La Rochelle.
Thank you. And thank you especially also for all your support to the group.
Okay. Now, Vincent Poulain d'Ambition from the soft will have some comments and say some words.
Thank you, Madam President. Thank you, Frank, for the nice presentation and the scientific quality of your document. I appreciate it. I've learned many things, and I realized reading the document that for our own systems, when we try to detect and extract zone in the document, we use a variation of the probabilistic context-free grammar. I didn't realize before it's really very close to what was being proposed by Canongo. So thanks to make me aware of these facts. The question, you are on the layout analysis, and a bottleneck or difficulty or an issue in the expectation maximization method is the initialization step. But the hardcore of the success of the method really depends on the quality of the initialization. Can you remind me the initialization we use?
In which kind of method?
Sorry?
In which method?
For the layout analysis.
Well, for instance, here only was required an initialization of the method based on the EM algorithm to fit the regions. So this initialization was based on learning the most common locations of the different regions that we want to model from the training set, and then initialize in the mean of these locations, using the number or an excess of the number of these regions, but it was related to the learned positions on the training set. For the rest of the methods, the initialization was not required a particular initialization. It was only for the method based on fitting regions.
And Joseph asked how we can combine. I was wondering if you can use your first method, which gives a raw idea of where are the information
to initialize
this model.
Yes, this can be a good initialization, better than maybe this. But the problem is that here you are being more suggested or conditioned to the good results of this initialization. So it can be interesting to evaluate this kind of the results obtained by one initialization or another. But yes, it can be used first segmentation or first detection of the regions in order to initialize and then find the optimal configuration of this particular region.
And if I move now on the line segmentation, on slide 7, I think.
7?
Yes, that's the method. Just 57.
57. Sorry.
You know, in the header, the address, the red lines, I suppose, represent the detected line. I was wondering if the 2 and the beginning of the second and third line are missing. It's just a representation issue, or there is a particular reason why it's not ready?
No, this is just a representation issue. For printing these lines, we took in consideration the parameters of the regression line. But then in the current model of the pixels of these areas will be merged with other kind of other pixels, and at the end, the final labeling, these pixels will have a higher probability to belong to this line. So at the end, the labeling of these areas is correct, even though in this representation, the extreme of this regression line does not does not fit this part. But at the end, the probability will be assigned to this line. At the same time, for instance, here, this area at the end will be connected with more pixels of this part, and will be also labeled with on this particular text line.
In your results, you notice a big difference in the quality results, on the performance results between the administrative corpus and, for instance, ICDAR corpus. It's close to 80%, and the other one is close to 97%.
Mm-hmm.
Did you analyze the reason why there is so large gap between the two corpus?
Well, actually, here we have some ground truth bias that many of these lines that we detect as text lines are not labeled in the ground truth. So in this case, using the metrics that we are using, we are being penalized in terms of numerical values by detecting this kind of regions. If I remember well, for this kind of, or this, we got some 60-something% of detection where the actual text lines are quite good detected. So in this case, the metrics is not well. It's just for having an idea of the overall performance of the method. But I think if we take into account this ground truth bias, the result will be better. So we observed a lot of qualitative results, and we were able to detect well many different configurations of the text lines.
Allow me a question or comment. I continue on this point. One weakness or one drawback on the, it's not a drawback, I think it's a weakness. In the method is, and the failures you have are for ascenders and descenders connecting to a line above or below. So the overlapping of this kind of information, and this is not, I understand it doesn't work because it is not modelized in the model. You suppose a Gaussian distribution, so it works fine for the center of the line, but it doesn't really model that it may happen to ascenders and descenders, or you consider as noise, because in the Gaussian distribution it's supposed to be noise. And when you have some connections where we see sometimes it works well, and many times the information is connected to the wrong line. I was wondering if the administrative corpus more issues in this kind of problems appears more frequently or less frequently than on the rest of the field. And the real question is, what do you suggest to tackle with this issue, or to join the good pixel and to cut as accurately as possible the connections?
Well, right now, regarding the amount of these cases in administrative documents, I think is less frequent. But since our handwritten annotations, you never can know exactly how the user or how the person is going to write. But this is the fitting process of the line. It takes more into account the central part. That is true. But then with the contextual information, I think of the Markov random field and the set of features that we are modeling, I think we are propagating good the information in order to be able to split these touching characters by probability. So the upper part of a touching character will have more probability to belong to the regression line that is crossing its corresponding line, and the lower part of this big connected component will have more probability to belong to the second line. So what we do is we detect these cases, and we cut without a not very intelligent way, but just cutting by distance. We are getting quite good results in the separation of these situations. So yes, I think as a future improvements of this method, this can be a thing to incorporate, and not only incorporate as a post-processing step, but also incorporating by modeling more intelligent feature functions within the probabilistic framework. I think some additional work can be done in that direction.
Thank you, Frank.
Thank you.
And in general comment that we exchanged and we meet many times in the last 3 years, in the last 4 years for this project, and I appreciate all the time of presentation and the talks, and I was impressed by the jump in performance between the result in 1913 on the competition where you were almost at the bottom, and with the new result where you are almost on the top. that was a great improvement. And I'm very pleased you joined us in our Regression to continue to work with us on other topics and new
Thank you.
And new challenges. I'm really pleased to continue to make it.
Yeah, it's very great for me as well. Thank you. I finish my presentation.
Thank you. So now I will give to Oriol Ramos Perales, who is the PhD director. So he has maybe some comments and questions.
Well, thank you, Laurence. Well, of course I don't have any question. We have got about 3-4 years to talk about your thesis. So I would like, I only like to say that thank you for the time that you have spent working on that. It has been a pleasure to me to work with you. I don't know if you think the same with me. But
I have a full stack of papers with formulas.
So congratulations, and you don't have any other questions.
Thank you.
Okay. So I will ask some questions too, some comments. So I was impressed by the number of approach you have tested. So many approach, more classical, less classical. And okay. I have a more general question for layout analysis. You have some kind of sequences, for instance, body name, body task, name, body task. So what do you think about new approach with recurrent neural networks that can analyze sequences very efficiently?
Well, actually, these recent neural networks are in all the tasks, but I think they are quite related to the modeling on probabilistic graphical models. No, so it is true that these are quite a powerful model that can learn from these particular features and dependencies always that you have enough data. But the good thing of using these probabilistic graphical models is that you can also include this type of information within the description of the model. Using convolutional neural networks, at the end you will be able to learn it, but maybe there are some things that go out of this learning process that can be relevant, or information that other people in the project, that historians or any other part of this project can apport to modeling this problem. And I think it has some advantages to use probabilistic graphical models, but I think that can be also quite important to try to observe the results using this kind of models, since they have been proven that the task where you apply this kind of models, you obtain very good results. So I think for future stages of my research career, I will do some work using this kind of information, but not forgetting about these probabilistic graphical models.
Because the advantage would be, for instance, not to define features.
Not to define and just configure the network and let it learn about this, and then seeing how you can define it better. But I think it's I'm not going to say it's more easy, but I think this using this kind of models allows to play more with the information and the different features. That is also good.
I have also a question about your related fashion, your features RLF. So they include context at the feature level, and the CRF, the conditional random fit score, also include context, but in a smaller neighborhood.
Yes.
So is it useful to use CRF because you have already context in the feature?
Well, it is useful to use CRF because the type of contextual information that are modeling the features and the CRF in this particular model of CRF that is just pairways, this source of information is different. In the case of the dependencies or the context that is modeling the CRF are just in a local neighborhood, and this is useful to produce smoothing areas that maybe using other kind of models is not possible. And using these relative location features help that the detected areas are better characterized and also reinforced by this contextual smoothing effect of the conditional random field. So I think it is good to combine these two sources, but the good thing of the relative location features is that they can be applied on any other framework.
About the evaluation, you compare with other approaches for text line segmentation, for instance. But if you are not at, how do they work? What do they do differently than your approach? For instance, the winner of the competition, what is different from their approach on your approach?
In our model, we have to take in consideration that we are just using a linear approach at the end that is reinforced by this contextual information, but at the end it's just a linear approach. The other methods, especially the top methods, had some more elaborated processes of merging or finding the correct path or the correct merging of the different connected components or any other unit that they have, or using these scene carving procedures. So their fitting process is more complex in terms of complexity of the model that they are using. Here we are just using this simple model and also using this simple feature level information that at the end we are just using information about the location of the pixels. We have not other information, other feature extracted from the textual part or analyzing the strokes. And many of these methods rely on this more specified analysis of the distribution of and the relations between the connected components, or minimization approaches, minimizing an energy of some fitting functions. So I think our approach is with a simple baseline model is able to get not the top results but quite good preliminary results. And then incorporating this kind of features, I think the model can be as powerful as this in this kind.
Because from the perception point of view, working at the pixel level is difficult for text line segmentation, because if you enlarge an image, you cannot find the text line. You see the text line when you are at a distance. So I don't know, but maybe the question was already asked by Jutta, working at a higher level, maybe could also or combine both local and global approach would be useful.
Yes, I think the best option is to combine two sources from a lower analysis at pixel level, and we have seen as we can get some good results by other more higher level features or descriptors that help to identify these touching characters that can be easily identified when you increase this vision, not from the low level but more in a high level description of the line. So I think combining this or including these new sources of information in that direction could lead to improvements.
I think that's all. Thank you.
Thank you. Okay. Thank you very much for your.
So now the jury will deliberate. So we ask people in the audience to go a few minutes out.
The procedure I explain you. Well, I have to collect our individual report reports